So it's great to be here. It's always difficult to choose a topic for these audiences that have broad capabilities. So I hope this is a successful one. In part, it's motivated by the work on the IPCC, which Larry mentioned. I lead the Ethics and Economics chapter, which is very easy to summarize in 50 pages. And another chapter, which I'm not involved with, is risk and uncertainty. And it is a lightning rod for a lot of what is going on in the IPCC, in the sense that it's expected that they answer all questions regarding what to do about climate change, boiling down the entire picture into a matter of risk, managing risk and uncertainty. And it's difficult to overstate how this permeates what the IPCC does. Consequently, I thought it would be appropriate to talk about this topic of uncertainty, in part because a lot of the work I've done has been on this area, but also I think that it's poorly understood. Most people know what uncertainty is, but if they don't quite understand it completely, they think that's okay because it is uncertainty after all. So we'll talk about that today. And I don't have too many pictures, but I always like to emulate the ecologist and at least start off with something. So here's a quote from a famous contemporary philosopher. Many of you at least everybody knows him, Donald Rumsfeld. I couldn't have said this better myself. It characterizes the fact that uncertainty is a complicated issue and making sense out of it is very difficult. So what I'd like to do is step through the different ways of viewing this problem, and I don't pretend that I'm going to be covering everything, and I'm sure some of you that work in this area will say, well, I've neglected an enormous area of scholarship. So here's a menu of the things that I want to go through today, and all of these will be gone through briefly. The first is uncertainty and risk, which of course is the simplest view on this issue of uncertainty and climate change. And there are some key issues that come up in this. One is that some uncertainty is quantifiable, and this is particularly the case in climate change, and some is not. By quantifiable, I mean using probabilities. And furthermore, uncertainty is multifaceted. There's uncertainty in the natural science of climate change. There's uncertainty in the damages of climate change, which is a mixture of natural science and economics. There's uncertainty in the costs of mitigating and of adaptation, things like that, which is a sort of a mixture of engineering and economics. And in fact, if you look at what the Canadians and what the Americans said in pulling out of the Kyoto Protocol, cost uncertainty was the dominant factor in causing them to back away from their commitments. Third point, uncertainty is different from stochasticity. Uncertainty typically means that there's something that's true, but you just don't know where the truth is. Whereas stochasticity is just a random shock that's constantly being applied to the system. And in the climate area, there's lots of stochasticity that you'll never know. Flipping a coin, you're never going to know whether it's going to come up heads or tails, no matter how much you study it. But a lot of what goes on in climate is uncertain in the sense that we can learn about it as we go along. And particularly for economics, who is uncertain, who learns, and does it matter? That's an issue. Is it the government that's uncertain and learning? Is it the farmer that's uncertain and learning? Or is it anybody in between? Second point, fat tails. A lot of people probably have heard fat tails discussed. It's a big issue. Probably one of the biggest issues to come out in the last 5 years anyway in the economics of climate change. And I'll talk a little bit about that, but simply put, as think of it as the temperature change from climate change increases, the damage grows more rapidly than the probability of that temperature increase. So if you do an expectation, you have the expectation, the expected value of damage is growing, and of course, if the support is infinite, you'll get an infinite expected damage, which causes all sorts of problems for figuring out what should be done about the problem. Learning is an overlay on uncertainty that actually is really what people are focusing on a lot when they focus on uncertainty. The issue is that over time, uncertainty changes, and as we learn about the problem, and some learning can be directed in terms of investing in R&D, incentivizing R&D, and some learning just occurs as time passes. We get another draw on the global temperature. We update our prior on what the distribution of what the probability is of different climates, and proceed. I'll talk about that in a minute. Risk perception. This is a problem that is difficult to deal with. A lot of people experience, some of the people that have been around as long as I have, remember the nuclear power controversies of the 70s and 80s, where people thought the risks from nuclear power were much greater than the technicians thought the risks for nuclear power were. So what should be used by a policymaker in making a public policy decision? And the same thing applies to climate. There are also lots of behavioral economics issues associated with risk and perception where people don't act the way one thinks a rational person ought to be acting. And do you change how a person acts, or do you change the way you analyze it? Irreversibilities. This is particularly important in the climate area. The idea here is that when you take an action and something irreversible happens, and then you find out that, oops, I shouldn't have done that, you can't back up again. If it's reversible, you can. And if it's reversible, you don't have to worry really about proceeding, because you can just back up if it doesn't work out. But in the climate area, as in a lot of environmental areas, there are irreversibilities which induce a precaution that you wouldn't otherwise see there. The evolution of future technology is highly uncertain, as many people in this room know. And how to understand that and represent that is crucial to analyzing the climate problem, because no matter what dimension of the problem people are looking at, relying on someone inventing our way out of it is a crucial part of most solutions to the climate problem. And then I'm going to turn to managing risk and uncertainty. I'll talk about decentralized management, which involves insurance markets and financial markets and some real options. And then centralized, which is the government investing in infrastructure and regulating. So that's sort of a menu of the things I want to look at one at a time. And it gives you a perspective that uncertainty in the climate context, but really in most contexts, is a very much more complicated issue than just writing a probability distribution for possible outcomes and letting that be the end of it. Okay, so let me first point out, and this I think has particularly relevance to climate, and I use Frank Knight because he talked about this almost 100 years ago, but we don't need to dress it up with a Knightian risk and Knightian uncertainty. Basically, the issue is whether probabilities can be assigned to different states of the world or not. And in the climate area, it's very easy to see this. Probability of rain in Des Moines on May 1st, 2013, or in Palo Alto for that matter, is something that's very easy to answer. There's lots of repetitions of that. The data's there that can be used to generate that probability. But there are other events where there's little data, and it's very difficult to compute a probability. And the examples given here, the probability of West Antarctic ice sheet collapsing in 2014, or the probability of North Atlantic thermohaline shutdown, Gulf Stream shutdown in the 21st century. There's no data to base that on unless you look at a paleoclimate record, but that's not terribly relevant to what we're doing now. There's no data to base this on. It has to be a subjective estimate of what is happening. And unfortunately, a lot of what's going on in climate fits into this category, which makes it tough to analyze. So here's a set of probability density functions, PDFs, but PDF, of course, has been taken over as a term by Adobe. But this is a bunch of PDFs for the equilibrium climate sensitivity. This is just taken out of the last IPCC. And most of the mass, you can see, these are different models, probability density functions from different models. Most of the mass is around 2 to 3 degrees. What the equilibrium climate sensitivity is how much the global temperature changes if you double the CO2. So it's a very rough measure of how responsive the climate is to greenhouse gases. And most of what people concentrate on are these 2 to 3 degree levels, or 2 to 4 degrees, where you can see a lot of the mass is. But there's a significant amount of mass way over here, too. And that's an issue in the fat tails debate. Now, it's interesting to ask what kind of uncertainty this is. These probability density functions are not based on data necessarily. They're based on a modeler's analysis of some inputs into his model, but not all inputs into his or her model. So these are subjective probability density functions, which makes it difficult to use them completely for analyzing uncertainty. Okay, so let me talk about fat tails a little bit, which is a little nuanced. It's not totally clear what is a fat tail exactly, but there are often it's viewed as there being 3 kinds of probability distributions. A thin tail, which corresponds to a finite support, so the support ends, so that there's not an infinite amount of mass underneath the distribution, or it doesn't go on for infinity. Medium tail, something approximating a normal distribution, and fat tail. The tail drops more slowly. So they all integrate to 1 under the distribution, but it's just as you go away from the mode, how rapidly it tapers off. And a good example that Bill Nordhaus gives in an article in the journal that Larry mentioned that I edit is the height of American women and earthquakes. Height of American women, the mean 64 inches, the standard deviation of 3 inches, and it's roughly very close to normally distributed. Now, that may not seem very profound, but the implication of that is that the probability of walking down the street and running into an 11-foot woman is about 10 to the minus 230. So you probably are not going to see an 11-foot woman. Now, if the distribution were different, you might expect that. Now, if you look at earthquakes, Seismologists tell us that it follows a fat tail distribution, power law distribution. And if you look at the 2011 Japanese quake, and you assume that it was a normally distributed, or the energy of quakes is normally distributed, then you'd conclude that an event like that should happen once every, that's not a minus, the probability is 10 to the minus 13. Well, you get the idea. Infrequently. But using the fat tail distribution and the historic data, you get a result that it's about once every 100 years. So the reason this is important for climate is that if we're talking about extreme events, if we're talking, for instance, a 20-degree change in or climate sensitivity, a 20-degree change in the global temperature as a result of doubling atmospheric carbon, if that's more like the 11-foot woman, we don't have to worry about it too much. But if it's more like the Japanese quake, then maybe we do need to worry about it quite a bit. And that's sort of a way of thinking about the significance of this. And if you look at that graph I had before, almost all of the analysis we hear about and we read about in the IPCC concerns changes in temperature in this region here. Rarely do we see an analysis, a very complete analysis of what happens with temperatures up here or even further, because the probability is nowhere near 10 to the minus 230 as we get out there. So this is the significance of the fat tail, that if damage from climate change has a fat tail and risk aversion is significant, then the expected value of damages is negative infinity. And which implies that all resources should be devoted to mitigating climate change. But this is a logical problem, because you can do the same analysis with meteors hitting the Earth or other things that become very big events, but small probabilities. So the implications of this are still a matter for debate, but that's the fat tail debate. Okay, let me talk about learning now. Learning, time passes, information is acquired, and I want to point out one of my favorite facts is that learning about a parameter may not, in fact, reduce the variance of your estimate. Suppose you have a normal distribution pretty tight, and you learn, tight around 0, and you learn the true value is positive and not negative. Now you have a posterior that's actually that has a higher variance than your prior. So learning doesn't necessarily reduce variance. Learning is an economic term that allows you to actually use that information to make better decisions after you've learned. So who learns? Individual agents, farmers. The example all climate economists like to talk about, farmers, because we've all planted our radishes when we were kids, so we sort of understand farming, we think. Regulators who make decisions about mitigation, and multi-agent decisions. These are, if you have a bunch of countries getting together and they're uncertain about the climate and they learn, it turns out that has implications for how easy or difficult it is to form an agreement on doing something about the problem. How does learning take place? Well, it can take place passively, as I mentioned. Active experimentation, this is very similar to what we're doing with the climate. Maybe a better example that's easier to understand is if you're a monopolist, in other words, you cornered the market, but you don't know what the demand curve is for your product, maybe you make candy bars. Well, you can sell your candy bars for 20 cents today. Tomorrow, sell them for $2. Day after, sell them for $1. And by putting these different prices out, you're actually collecting data that helps you learn about your demand curve. Well, in the climate area, we're putting out a lot of carbon. We're seeing how the climate responds over time. We'll learn. And then R&D, where you actively acquire information, is a third way of learning. Okay, so here's a simple representation of passive learning. Suppose the truth, A is your prior, this is where you are, this is simplex. So this triangle just means the three probabilities add to 1, so it has to be somewhere in this triangle. And if this is where we start, there are the three states of nature. We don't know which is going to, which is the true state of nature that we're going to end up in. And our prior assigns probabilities to each of these three states of nature. Now, as we learn, we will end up at one of the vertices of this triangle, corresponding to learning completely which is the true state of nature. And as we learn, we'll proceed out one of these three rays. We don't know in advance which direction we're going to go, but we are able to represent the process of learning and the probabilities associated with learning in this simple way, and then integrate that into the economics of the problem. So I have several papers that use this representation of learning. So here's an example of a regulator learning. A regulator perhaps is uncertain about climate sensitivity, as they certainly are. The Republicans think it's, this is oversimplification, but the Republicans in Congress think the climate sensitivity is low. Some of the left-leaning Democrats think it's extremely high, and there's uncertainty about it. Each year provides more data on climate, the distribution of the weather, and the regulator decides on regulatory actions with this uncertainty, but also knowing that she'll know more than a decade. This is an important issue because you can act today or you can defer your decision to act tomorrow. And the regulator can also take action to change learning by investing in R&D. Now that's a common theme you hear in Washington. Let's not do something about this problem X. Let's study it some more and invest in R&D, and then take action. So the regulator has a clear, or you can promulgate regulations to accelerate learning, such as fuel economy standards, which accelerate the process of learning about fuel efficiency in vehicles, or banning incandescents, which make people scramble to get better LEDs, for instance. So this issue of the regulator learning and taking action or not taking action is a very, very important one. Let me give you the other side of this example of farmer learning. So this is a map, which some of you may have seen before. It's from a paper by Mendelsohn et al. And what this is the value of agricultural land. There's no climate in here. You know, we all have an idea that we think we know the difference in climate between here and up there. This is just the value of agricultural land. And we see that if you look down here, the stuff that's red through blue is below average, and the stuff that's yellow or brown is above average. So roughly speaking, the top half of the countries has more productive land than the lower half of the country. And you could think that is due to climate, and you could study it as a result. So one view on adaptation and adjustment on the part of the farmer is that you think the farmer can instantly change cropping in response to climate change. Let's make that assumption. And the second point we're going to assume is that climate is unobserved. This is a very important assumption that is often overlooked. We never see climate. Climate is not something that you can see. Climate is a distribution of weather. You don't see distributions. Nobody sees distributions. And the problem is the farmer does not observe the climate. Only after experiencing a change in the climate or reading an IPCC report or a National Academy report will the farmer start to change his prior on what the climate is. And in the meantime, there'll be lots of impacts and losses as the farmer adjusts to a new climate. So if it's all driven by uncertainty, climate changes, but the farmer can't observe the changed climate, makes mistakes, racks up losses, eventually figures out after it's been flooding, his bottomland's been flooding for the last 50 years, he decides maybe it's going to flood for the next 50 years, and he changes to rice. Now, so that's a uncertainty view of adaptation and adjustment. And plus these transient costs, which are these temporary costs that occur as you learn about what's happening to the climate. I should point out that some action may be precautionary. If you think that drought may be coming to the western United States, like everybody says, you may invest in irrigation so that if it doesn't rain, you're okay. So at a cost, you can reduce your vulnerability to this uncertainty. And here's a little graph, time along here, the value of an acre of land. Suppose we start out here and then we instantaneously change the climate, but the farmer can't see us do it. The value of that land's going to drop because the farmer continues his old practices, not knowing the climate has changed. Eventually, the farmer adapts and adjusts and comes to the new equilibrium value of the acreage. And in the interim, this is the transitory or adjustment cost that the farmer loses as he or she adjusts to the new climate. And it's easy to take this example and apply it to coastal flooding, where you rebuild a house time and time again until you realize that maybe I should move inland a little bit. That transitory component that comes from not being able to truly observe the true state of the world can be very significant, and it's induced by uncertainty, this example. Okay, so the source of these adjustment costs is that weather is rarely average, as we know. It was really windy today, hasn't been windy for a while. When weather turns out differently than expected, you can either say, well, the weather is variable. Just keep doing what you did. But when it is different, your farm profits suffer, or they can suffer. They could go up, actually, if you've got an unusually wet and warm winter. And basically, in the end, everything re-equilibrates. So let me just mention briefly a paper that I did with colleagues a couple of years ago. We empirically implemented this by observing annual profits as a function of farm characteristics, weather expectations, which are based on the climate measured from the previous 30 years, and actual weather. Estimated how, in fact, climate and weather interplay to generate profits for the farmer, and then examined the counterfactual. This counterfactual, it's a term economists use, change the truth. Suppose the climate were to change a lot instantly, but nobody knows it. Then what would be the loss? And using a standard 3-degree change increase in temperature and an 8% increase in precipitation, which is perhaps not the right assumption, but this is a counterfactual. You find that there's about a $3 per acre gain in value of profits, but an adjustment cost of $1.38 per acre. So the net impact is about half of the gross impact. So the adjustment costs are an important thing to do to water down the net impact. Now this says that there was a gain in the median county from this climate scenario. Of course, you can pick a different climate scenario and you get a loss. That's not the thing to focus on. The thing to focus on is that the uncertainty really changes the way you look at this particular problem. Okay, now moving on to perceptions of risk. This is a figure that I've always liked. It's an old figure from Slovak, but it's reproduced it in my textbook. This is a bunch of people were asked about these common risks. You know, what's your probability of getting botulism, for instance, from eating in one of the Stanford cafeterias, or tornado front, or getting shot. And of course, you have data on the probability of all those things that's readily available. And it turns out that if this is the true frequency and this is the perceived risk, that low risks are really overestimated and high risks are underestimated. So that's something that many of you may know already, but this sort of snapshot characterizes problems associated with looking at individual preferences regarding climate change, risks of climate change, and trying to put together public policy based on that. You know, what do you use? Actual risk or the perceived risk? And it's maybe easy to answer that for something where you got lots of data, but what about other things where there's not a lot of data, so the true frequency is more difficult to identify.
The frequency is the inverse of the number, unfortunately?
Yeah, this is, that's, I think in a year, this is the number of, thank you, that's poorly labeled, the number of cases in a year in the United States. So the question is asked, what do you think the number of cases is in the US in a year? Okay, irreversibilities. Now, I mentioned a little bit about this earlier on. This came out of a paper by Arrow and Fisher back in the 70s, which was basically induced by the dam on the Snake River in Hell's Canyon. And the cost-benefit analysis on damming the Snake in this pristine canyon, although I've never seen it, but I take their word for it that it's a pristine canyon. The costs and benefits showed that it was worthwhile damming it. But there seemed to be something wrong with that logic, because if you dam it, it's gone forever, or more or less forever. You remove a dam, you really don't get the canyon back very quickly. You dam it, it's gone forever. Now, that's not an issue of uncertainty, because you can take uncertainty into account and still come up with the expected costs being less than the expected benefits and decide to go ahead with the dam. But the point is, under some states of the world, for instance, it turns out to be really, really popular to take whitewater rafting trips in western rivers in the year 2100. Under some states of the world, you're going to be sorry you dammed that river. And because of that, there's a value of waiting until you know more about the problem, sort of like an option value that needs to be figured into a cost-benefit analysis. And the same thing applies in climate change. You have abatement equipment, which if you prematurely invest in a lot of things to reduce CO2 emissions, but it doesn't turn out to be a big problem, that's an irreversibility. But a bigger one is that CO2 in the atmosphere, basically, if you put it up there, you can't suck it out very quickly. It's up there for a long time. And these two irreversibilities go in opposite direction. The abatement equipment reversibility favors deferring action, and the CO2 in the atmosphere favors accelerating action. And different calculations have determined which one is stronger. Let me just quickly put this up. I'm running out of time, so I'll just go through it quickly. Active learning R&D, there's a lot of climate policy sort of requires somebody to invent an easy way of decarbonizing the economy through invention and innovation. And of course, you can spend money directly on that. The government can double the Department of Energy's budget. But there's, as a number of people have determined, including Roger Knoll here at Stanford, the record of payoff for this direct expenditures on R&D by research labs is not all that great. So another way of doing it is to incentivize it by having a carbon tax so that inventors can actually see a benefit from their innovation. If carbon is not taxed, I invent a way to reduce carbon. Who cares? Who wants to buy it? Nobody. That's an exaggeration, but the payoff is much smaller. There's also the golden carrot, which was used for refrigerators in the last decade, I believe, or in the 90s. This whole area is poorly understood in terms of its effectiveness. Okay, so let me turn to the last topic, which is managing risk and uncertainty. And first talk about the decentralized management of this. There are three real ways of doing this. One is with insurance markets. Some risks are insurable, as we all know, home fires, and some are not, like unemployment. You can't really buy private unemployment insurance, not that I know of anyway, because only the people who are about to get sacked would buy it. Sometimes institutional change is needed. You know, it turns out in the U.S., much of the damage from climate change will be in coastal flooding. And a lot of that is because the insurance markets in coastal areas are distorted by a lot of institutions that push it in multiple directions for multiple social purposes. It reminds, you know, I was talking with a guy from a risk management agency in London about this, and he pointed out that in Bermuda, where insurance is priced, I'm talking about flood insurance for houses, is priced actuarially fairly, you can buy any kind of flood insurance. And if you want to put your house right next to the ocean, the premium may be 5% of its value per year. The result of that is nobody puts their house next to the ocean. They move it in. You know, the people that take risks respond to having paid a lot for insurance. In the U.S., we have other reasons for subsidizing flood insurance, but it tends to exacerbate the damage that may be caused from a rise in sea level. And just right here in River City in California, you know, one of the big impacts of climate change is on the snowpack in the Sierras and the water storage that goes with that. And the problem is that we have a shortage of water. But the shortage of water in California is in part brought on by the institutions where we send a lot of it to flood irrigate hay fields for horses that probably right around here actually, but also all up and down the California coast. So institutions are interplaying with damages in climate change. Financial markets, back before derivatives got a real bad name, catastrophe bonds were, and still are, I believe, a way of ensuring or basically hedging a risk by buying a security that pays $1 if something like the global average temperature rises X in a given year and nothing otherwise. So basically you can put that together with insurance to hedge a risk. And then there's also real options, which basically mean you buy real equipment that reduces your risk. The irrigation I mentioned earlier that reduces drought risk is an example of that. And then managing risk and uncertainty from a centralized point of view. Mitigation is an obvious way to reduce risk, but it's best if accompanied by a carbon price incentive. Adaptation, another way of reducing risk. Public investments to ameliorate possible consequences of climate change, but those should be focused on public investments like roads, power systems, things like that, not private investments. Institutional reform, I mentioned flood insurance and water in California already, and then I'll just mention international agreements where uncertainty can make agreement easier. This is a literature that goes back a couple of decades. The last slide I want to treat before I get to my conclusions is the treatment of uncertainty in climate analysis, climate models. Some of the students posed this question to me before, and I thought it was a really good question. So there are several types of uncertainty in climate models, and by climate models I mean both the general circulation, physical science models, as well as integrated assessment models or the whole variety of models. There's parametric uncertainty where you're not sure about a parameter like the climate sensitivity. There's structural uncertainty where you're not sure, is this, did I put this, this piece of furniture together correctly or not? And then there's stochasticity, which is, I've already mentioned, is the noise that's overlaid on all of this. Now, the simplest and most common analysis of uncertainty really is a very limited analysis of uncertainty. It's, you stipulate a probability distribution for key parameters and then just run a Monte Carlo analysis of what the outcome is. The problem is if you have endogenous decision making on that, the decision maker is actually making a deterministic judgment at every draw from the distribution, which is not the way a decision maker operates under uncertainty. Structural uncertainty is very tough to get a hold of. If anybody's put together furniture from IKEA, the easiest way is to go look at how it's supposed to be put together. But if you don't know what the true model is supposed to be for what you're working on, it's more difficult and pretty uncommon to actually endogenize decision-making under uncertainty in a climate model. And having that change over time as learning takes place is even rarer. And usually when these layers are added, everything gets simplified to make it manageable. And I just want to be fair about this. These are tough problems, so the modelers are not necessarily to be faulted from this. In conclusion, risk and uncertainty in learning pervades climate. It's ubiquitous. One conclusion is that don't look for most likely consequences of a doubling of greenhouse gas. It's remarkable how the lamppost story works. Everybody looks under the lamppost because that's where the light is. Most people focus on what happens for likely scenarios. But one of the problems in doing economics of climate change is that looking for that smoking gun has been really difficult. You get a few percent change in agricultural productivity from a temperature change. Well, that's not good, but it's not the sky is falling. And a lot of that is probably due to focusing on the most likely outcome rather than these extreme tail events. And if you try to focus on those extreme tail events in your analysis, you find that nobody's really looked at them in a comprehensive way. Third point is let the value of information drive further research. It's surprising how the research is driven by where the money has historically been or where the researchers happen to be that suck up all the money, rather than being driven by what's needed to make better answers. Now, this is a self-serving point, that the focusing more on the economics of climate change, the cost of mitigation and adaptation, and the consequences of a changed climate is really where we need to focus now that other things have been resolved to a certain extent in the physical sciences area. Let me close with this. And thank you.
So we've got a little more than 10 minutes to open up for questions, and I've been encouraged to invite students to really ask their questions first, and the more seasoned researchers can have a chance too. So, students in the class, what questions might you all have? Yes?
Yeah, it might be a little bit off topic, but so one thing that I was kind of missing a little bit is the idea of short-term consequences versus long-term consequences. And where you're talking about how people tend to estimate like low probability events, like they tend to estimate them higher than they actually are, then I would kind of assume that they would estimate short-term consequences to like occur with higher probability than they actually are. So that kind of seems like paradoxical to what's happening in the world.
You mean, I'm not exactly sure what you mean, but you think something is going to happen in 3 years, they would overestimate the likelihood of that than something that's going to happen in 50 years.
Yeah.
You know, there are a lot of things that are like that they aren't fundamentally an uncertainty issue, which I've glossed over. That's probably true, although I'm not sure that that's sort of a combination of multiple findings. So I'm not sure that's true. You know, maybe there's evidence on that, but I don't know. There certainly is evidence that people discount at declining rates as they go forward in time, but not necessarily for an uncertainty reason.
Yes, in the back.
I actually have 2 points to make. First is, from pure decision analysis theory, I've heard you talking about decisions and I've heard you talking about uncertainty, but I'm not sure I've heard you talking about risk attitude. So when you talked about the uncertainty tails and the fat tails, and you said we need to focus more on those, in my mind, your decisions are not only driven by the uncertainty, but they're also driven by how risk-averse or risk-seeking you are. That's how you basically put your weights on those uncertainties. So the data is the data. If this is what the climate models is giving us, then this is the data that we have. But how we respond to that data is not only driven by the probabilities, but it's also driven by the decision maker's risk attitude. So I want to hear your thoughts of how important that is. And then the second point is on...
Why don't we take that first one, because I'll forget what your first point was. You know, in the fat tails slide, which I went through pretty quickly, the bottom line was that that if the damages have fat tails and you're relatively risk averse, that of course can be quantified. Then you get an infinite expected damage, negative infinity expected damage. So the risk is an important part of that. And you had a second part of that first part?
I wanted to know your thoughts on the different ways of mitigating risk, because I noticed that 3 of the points that you've mentioned were more on the economic side and one of them was more on, if you want, the engineering side, me speaking as an engineer. But for me, for the first three, it's basically a cost transfer, right? Like I'm moving the cost of the risk of climate change from me as a corporation or from me as a farmer to the insurance company. So I'm just transforming or transferring that cost. Whereas if I'm actually using actual mitigation options, I'm reducing that risk altogether. So where do you see the trade-offs between these?
Well, that's true about the first, but if it's an insurable risk, that's still a very virtuous thing to do, because really we're pooling it amongst us, so that basically it takes advantage of risk aversion to reduce our turn our individual exposure to a big risk into a certain payment, which is much more attractive. And the other part of your question has, can you explain what that is again?
I just feel that with the risk, with the actual engineering.
Oh, the engineering, yeah, it's the engineering. Well, the technologies to reduce risk are like the example of irrigation, which is a simple-minded example, is certainly there. You know, I think that technologies that are available to eliminate the significance of risk. In the case of irrigation, it's the risk of a drought. And there are other risks, though, that technologies could, in fact, reduce the risk. It's a form of insurance. You're paying a certain amount to reduce the risk. You're paying for the technology to get the risk reduced.
Can you clarify the importance of making the assumption that the farmer does not observe the climate when you're trying to estimate agricultural productivity?
Well, it's the key part of that. If the farmer observed the climate instantly, then there'd be no adjustment costs, because the farmer would instantly adjust.
So that would be perfect adaptation?
Well, the farmer would adapt. Yeah, perfect would be a good term. I don't know if there's a technical definition of it, but basically, let's say let's say that it's a Central Valley farmer that's been planting grapes, and the climate changed, so rice is the best crop. Well, if he sees it instantly, he's going to plant rice immediately. If it takes him 10 or 20 or 30 years to realize that rice is now the best crop, then he's going to lose a lot of grapes in the meantime, and that's where that loss is going to be. So it's the essence of it is imperfect observation of the climate. And you come right down to it, this is a fundamental characteristic of the climate. Our basis for knowing that there's climate change is very noisy. We rely on the natural scientists to tell us what's going on. But just relying on our observation of the weather would be very difficult to tell, in fact, that the climate has changed. And a farmer, you know, they're used to having their crops spoiled by natural variability in the weather. So that's an essential part of that analysis.
We can take questions from anybody at this point.
If you want to know what the climate is here, you just drive up El Camino and go to Redwood City. You can see the sign that says, "Best climate by government test." And otherwise, you can look into real estate values on the peninsula as well. That tells you what it's like. But my
So
question,
why has Redwood City got lower prices than Palo Alto?
well, because government is rent. So the question I have is, the IPCC is often criticized, and it's a bureaucracy, and we understand that.
Sure is.
And it's used as a whipping boy. So I never argued with somebody who's talking about the IPCC. I just say, forget it, I don't care about the IPCC. But it seems to me that some of the things that are being missed, and I just want to ask you if this is true. Your reference to what's structural really comes down to engineering system. What goes into what, that affects what, what's the feedback system, what's the architecture of the actual overall climate system on the Earth. And more than just the climate system. So what is the IPCC or anyone that you know doing with regard to ocean acidification? Because that's more imminent and more nonlinear and affecting over 1 billion people within a couple of decades if we don't get things straight. So what is going on with ocean acidification?
Well, I don't know the answer to that. It's IPCC is a bureaucracy. It's a big bureaucracy, and that's in a different department that I'm in. That's in Working Group 1. And they do the best job of all the working groups, I think. But so I don't know the answer to it. It's a good question.
Yeah, ocean acidifications assessment group 1 and 2. So I guess
1 and 2 as well.
1 and 2 on the PAOs, but I guess I was wondering if you could talk a little bit more about what effective presentation of scientific information, both in the primary literature but also in assessment context, looks like beyond just, not just focusing on most likely outcomes, doing full range, looking at low probability outcomes. In an ideal vision of the world, what would the science look like to inform decision making and uncertainty?
That's a really good question. Let's just focus on damage from climate change, because you could repeat the same thing in lots of different pieces of climate change. And one of the problems we've had on our chapter in the IPCC is that the estimates of the monetary consequences of a change in temperature don't go beyond 6 degrees that we can find in the literature. And one of the reasons for that is that the estimate of the physical consequences of climate change typically don't look at what happens with a 20 degree or a 10 or 15 degree C change in climate. If you don't have the physical effects, you can't get the economic effects. And to be fair to the physical damage assessors, this is a big world, and there are lots of pieces to look at, and you can't, you're adding a dimension to the problem that just makes the task even harder. So I think that's the main problem, that there's just not enough analysis of those outliers. It doesn't have to be a big outlier. 8 degrees is maybe, it may sound big, but it's not that big compared to 15 degrees or 20 degrees, which has non-negligible probability there.
We've got time for one more question. Anybody?
Yeah, the question about the equity of damage. So you mentioned quickly how uncertainty can perhaps help countries agree on things if they don't know what's going to be okay for me, perhaps. And I was wondering, in terms of equity, like the farmer example, if someone has poorer access to information or poor education, they might be able to less adapt than others. So I would say, have you looked at what's your opinion on the distribution perhaps of incomes and education leading to different effects?
Well, if a farmer in the U.S. Is not up on things, then maybe he should go retire. But the question really applies to developing countries, where you really can't expect a subsistent farmer to know what's going, to be up on things, and furthermore, able to absorb a shock like a farmer in a developed country. So a lot of the adaptation that would be automatic with in the U.S., for instance, or Western Europe, the farmer changes practices, things like that. You may not be able to rely on it happening automatically in the poorer countries, and there may be a need for some proactive adaptation there.
Does that create some kind of counterbalance to the uncertainty leading to better agreements?
Now, the uncertainty leading to better agreements is very, very simply put that if you and I are negotiating, and I don't really know if I'm a winner or a loser from climate change, and you don't either, then we're more likely to reach an agreement than if you know you're a winner and I know I'm a loser. Then it's going to be tougher for us to reach a decision. Now, you can expand that to more than 2 people, to a group of countries, but you can see that the logic in that.
All right, well, Charlie, I think you're going to stay around for the food and drink, right?
Food and drink,
I can ask questions then. Can you all join me in once again